This is the data sheet of LPC2148 microcontroller, and this is the block diagram of LPC2148 microcontroller. This is an LPC2148 microcontroller's block diagram. So the king inside this microcontroller is my processor. With respect to LPC2148, ARM7 processor is sitting inside here. Hence, LPC2148 is called as ARM controller, ARM based microcontroller. Okay. So, for an embedded engineer, it is mandatory for us to check whether the controller given to us is working or not. To check whether this controller is working or not, it is mandatory for us to write a code for blinking of an LED. That is what we are going to do it with LPC2148 today. So the screen that what you are seeing is a block diagram of LPC2148. In this block diagram of LPC2148 microcontroller, there is an ARM7 core, which is ARM7 TDMIS, which is T stands for TOM, D stands for debugging facilities, M stands for hardware multiplier, and I stands for in-circuit emulation facilities. To check whether this ARM processor is working or not, only way for the user is to communicate with the processor only through ports. So with respect to LPC2148, we have two ports, port 0 and port 1. Port 0 contains 32 I/O lines and port 1 contains 16 I/O lines. Only through ports we can able to communicate with this microcontroller. So we are going to bring out the data from the microcontroller, and we are going to write a program for blinking of an LED. When it blinks, then that justifies the microcontroller is working. That is the place we have to start. Whatever microcontroller we have with us, so writing the blinking code. So blinking code is the first and foremost requirement for an embedded engineer to check whether the microcontroller is properly working or not, or whether the controller is in our control. Okay, how do you say the controller is in my control? When I write code for blinking of an LED, if it blinks, that justifies controller is in my control. All of us know very well control means on and off. To switch on the particular appliance, we have to send out logic 1. To switch off the particular appliance, we have to send out logic 0. After installing Keil Microvision 5 Keil IDE, so we have to double click this Keil IDE. Once you double click, some blank screen will come. And as usual, what we do, we have to create a new project. So as usual, you can go to the project menu, and then you can create a new microvision project, right? You can create a new microvision project. So in here, I have some ME class and LPC2148. So we have to create a new folder, creating some folder. Within this folder, as Abdul Kalam rightly said, we have to dream means this is my dream program, dream project, my project, because the project file, we are creating a new project as usual. So the project is dream project. So I am creating a dream project or ARM dream, ARM processor based programming. So I am saving this ARM dream, and the window called select device for target 1 comes. So the select device for target 1, from this window, here we are supposed to select LPC2148 microcontroller. So there is a company called NXP. So in this NXP, we have to search for LPC2148. So I am searching for LPC2148 and I am getting LPC2148. Okay. So this is the controller that we are going to use. So when I select LPC2148 microcontroller, the description window shows the entire block diagram, or what are all the internal peripherals of the LPC2148 microcontroller is clearly visible. As we all know very well, ARM7 TDMI based high performance 32-bit RISC microcontroller with thumb extensions, 512 KB, 512 kilobytes of flash memory with in-system programming and in-application programming facilities, and 32 kilobytes of RAM and vector interrupt controller with two 10-bit ADCs with 14 channel, and one USB with full speed device controller, and two UARTs with one full modem interface, and two I2C serial interface, two SPI serial interface, two 32-bit timers, and one watchdog timer, and a PWM module, and a real-time clock with optional battery backup, and Drono detect circuit, and general purpose IO pins, and CPU clocks up to 60 MHz, and on-chip crystal oscillator, and on-chip PLE. So these are all the facilities available inside the LPC2148. That is what the block diagram shows. Okay. Soon we select the microcontroller. So the internal features are briefly given in the description column, just for us to understand. Okay. This is the controller we are going to use. So I'm just clicking OK. So I have chosen the controller for my project, and it is asking that whether I have to add the startup files for the project folder. Yes, we have to give yes. Once if we give yes, so in the top left corner in the project window, there will be a new folder called target 1. And if you click that plus mark, So source group 1, there is something like source group 1 will come. And again, if you click the plus mark, startup.s file is there. Okay, so we have created a project, and the project name is Dream ARM. Okay, so I'm dreaming about ARM processor. That is what my project. And the project is ready. And for this Dream ARM project, I have chosen the microcontroller, which is LPC2148 microcontroller. That is what we did up to now. Okay, now I have to create a new file, right? So for that, I am going to the file, and then I'm going to create a new file, and then I'm saving the file with an extension .c, because we are going to write a C program. Okay, for all of our convenience, right? It is very complex to do assembly language programming with ARM processor. So it is convenient for us to write a C program, because all are comfortable with C program. Hence, I'm going to write the C program. So I'm going to blink. I'm going to blink the LED. Hence, I'm giving the file name as blink.c. So with extension .c is very important. So that file is saved, right? After creating a new file, I'm going to save the file in the same folder, LPC2148 programs. Automatically, it is coming to the folder. So in that folder, we have created a new file, and we are saving that file with an extension .c, which is blink.c, and then I'm saving this file. Okay, so blink.c file is ready, and I have to add the file to this project. Now I have only one file, which is blink.c. So to add the file to the project, I have to take my cursor to the source group 1, and then I have to do the right click, and then add existing files to group source group 1. So here it will automatically take us to that folder that what we have created right now. For that convenience only, we are creating a new folder. So we have only one C file, which is blink. So I'm selecting this blink.c file, and I'm clicking add. Once if I click add, so that file will be added to this project. So this is a way we have to add files to the project. So whatever file we are adding to the project, that file alone will get executed. Okay, which file need to be executed? That file need to be added to the project. So this is how we have to add the file to the project, as we all know very well. So we are going to write our first program in ARM processor, right? As because it is a C program, as we know very well, C program starts with hash include, right? Okay, because we are writing in embedded system programming, hash include, it is not about hash include stdio.h. If it is stdio.h, it is related to the Intel Core processor that what we have in our PC. And because you are writing in embedded system programming, so already we have an experience by writing it reg51.h. What is reg51.h? It is the header file. We are including the header file for the 8051 microcontroller. Similarly, with that understanding, now we are going to include the header file for LPC2148 microcontroller. So hash include LPC2148. Okay, R214X. In general, we can say LPC214X.h is our header file. And as we all know, because we are writing an embedded C programming, the universal syntax is void main. As we know very well, void main is the fundamental C programming format. And because it is embedded system programming, while one is mandatory, hence I am giving while one. While one is mandatory, hence I am giving while one. So this is the format for all the embedded system programming, whether it is 8051, whether it is LPC2148, or etc. When we are writing our code by ourselves without any board support package, this is the best way to start working with this coding, right? That is why it is being insisted now. Okay. So normally when we use 8051 microcontroller, we used to say port 0 equal to 1's complement of port 0. This is what the usual step that we used to follow. But here we are using LPC2148 microcontroller. So what is the syntax for that ports? Something like that we need to understand. So for that, it is mandatory for us to look at the data sheet. That is why I keep on insisting to look at the data sheet. Now I am just taking you all to see the data sheet. So in this LPC2148 data sheet, page number 7, we have a block diagram. GPIO is a parallel port, which is in page number 80. And we have to go to page number 80, and then you have to check the data sheet. And it is mandatory for us to look at the features of this general purpose input port. With respect to LPC2148, we have a GPIO with these features. What are those features? Quickly to refresh. Every physical GPIO port is accessible via either a group or registers, providing an enhanced features and accelerated port access at the legacy group of registers. At reset, all the input-output lines are connected, will become an input port. If you want to send out the data, we have to use the direction control register in LPC2148 to configure the port as an output port. That is what. So backward compatibility with other earlier devices is mentioned with the legacy registers. Okay. So this is the simple feature. At least we have to look at the features in the datasheet. That's why I am highlighting here. Okay, and the applications are, it can be used as a general purpose input. For example, it can switch on the motor or switch off the motor. It can switch on the lamp or switch off the lamp, or it can open the door or close the door. Wherever there is a control applications, like on-off applications, we can use general purpose IO, as we all know very well. And it is used to drive LEDs or other indicators, controlling off-chip devices, and sensing digital inputs, something like that. So any inputs, it can come only through ports. Any output, it can go out only through ports. Okay. So this is one you need to understand. And there are two ports, port 0 and port 1. Port 0 contains 32 GPIO pins. Hence it is 0.0 to 0.31. Port 1 contains 16 GPIO pins. That's all. Okay. So P1.16 to 1.37. This is, doesn't mean that port 1 is 16-bit port. Port 1 is also 32-bit port, but there are 16 pins are available due to the limitation of the pins, right? So say for example, if you go to the pin diagram, so this is quad inline package, right? LPC2148 microcontroller has quad inline package. What do you mean by quad inline package? In all the four sides we have pins. With respect to 8050, there are only two sides we have pin, which is dual inline package. And always the pin numbering is only in the anti-clockwise direction. There is a circle in the top left corner. There, that is the indication of the first pin. So 1 to 16 in one side, and 17 to 32 the other side, and 33 to 48 other side, and 49 to 64 other side. To minimize the size of the chip, they have freezed the pins only 64 pins. If two ports are being used fully, all the 64 pins will be occupied by the parallel port itself, and there won't be any pin for crystal oscillator, there won't be any pin for VCC and ground. Hence, they have reduced the port 1 pins to 16 pins, where port 0, exactly speaking, 32 pins, and port 1 16 pins. So 32 plus 16, 48 pins. So 48 pins of the 64 pins are used as general purpose input output, and the remaining pins are used for VCC, ground, etc. I hope you have understood, right? That is why there are only 16 pins in port 1 and 32 pins in port 0. So these are all the four registers. IO pin, input output pin is one register. Input output set is one register. Input output direction is one register. Input output clear is one register. So with respect to LPC2148 microcontroller, there are four registers associated with each port, among which IO pin is one register, IO set is another register, and IO DAR is another register, IO clear is another register. Meaning there is a pin register, and there is a, for setting the corresponding bit, we are using IO set register. For clearing the corresponding bit, we are using the clearing register. And there is a direction control register which sets the direction as input or output. That is the one we need to understand. Those descriptions are very clearly given in this description column. And there is an access column. So from this access column, what you understand here is, whether it is rewritable. Yes, I can read from that register, or I can write into that register. So IO pin is rewritable, IO set is rewritable, IO direction is rewritable, and IO clear is write only. So we can, WO means write only. That is very important. At reset, what is the value of those registers, which is very important. At reset, the value of those registers are 0, 0, 0, 0. So if you observe carefully, 0x 0, 0, 0, 0, 0, 0, 0, 0 means x denotes it as hexadecimal. So because it is hexadecimal, every 0 is a nibble, right? Every 0 is a nibble. Nibble means 4 bits. Okay. So there are 8 zeros. That means there are 8 nibbles. So 8 into 4 are 32 bits. So all the registers are 32-bit registers. Hence you can represent it with 0x followed by 8 digits. That's very important. Each digit is a nibble because it is a represented as 0x, which is hexadecimal number. So IO1 pin is at reset value, it is not applicable, right? So, but IO set is 0, and IO clear direction register is also 0, and IO clear register is also 0. Okay, so this is very interesting. This is the memory map location. E0002 8000 is the memory map location of IO 0 pin. Okay, memory map registers, right? So this is the memory structure, and port address and name, right? E002 8010 means it is port 1. That means there are two IO pin is common, right? Input output pin is common. Please look at the screen, which is very important. IO pin is common. That means input output register is common. But there are two ports, right? For port 0, IO 0. You see IO pin in general. For 0, IO 0 pin. and for port 1, IO1 pin, something like that you have to represent, right? Okay, this column, I'm showing, look at the screen, look at the cursor. This column is for port 0, and this column is for port 1, and these are all the locations. E002 8000 is IO0 pin, and E002 8010 is IO1 pin. This is the one you need to understand. Similarly, there is a set register. For port 0, there is one set register which is IO0 set. For port 1, there is another set register which is IO1 set, which corresponding memory location is this, which is in memory mapped register. And there is a direction register. Port 0 direction register is IO0 DIR. Port 1 direction register is IO1 DIR. Port 0's clear register is IO0 clear, and port 1 registers clear register is IO1 clear. So these are all the 4 registers, and its associated memory mapped locations are also shown here. So at least we need to look at the register values as well as the features before going to write the program. Okay. So going to the program, this is what we did with 8051, but nowadays we are working with ARM processor core. So what I'm trying to do is I'm going to write a program for this. So IO input output 0, let us assume I'm using input output 0, port 0. So IO0 pin equal to 1's complement of IO0 pin, let me say. So I'm blinking the port 0 pin. I have written the code for blinking port 0 pin. Look at the screen, look at the cursor, right? So this is the syntax for port 0 pin, IO0 pin. So by understanding that from the datasheet, we are using the same syntax here. And as usual, I am just compiling. It gives 0 error. Then building, it gives 0 error. Then I am debugging. Start stop debug session, right? After compiling debugging, and I'm stopping debug session, and it is coming to the debug window. So this is the register window. For ARM processor also there is a register window, but here if you observe carefully, all the registers are 32-bit, right? So 0x4000 0060. So there are 15 registers. As we all know, there are more number of registers in the RISC architecture. In the programmer's model, in the ARM programmer's model, you can see there are 15 registers, R0 to R15. So those R0 to R15 registers are very clearly visible in this ARM processor simulation window. This is very important features of Keil IDE. The purpose of introducing Keil IDE is it is very easy for us to view the register content more comfortably in a more beautiful way to understand. That is why Keil IDE is chosen and Keil IDE is being discussed. Okay, so there are 15 registers in ARM processor, as we all know very well. Whether it is ARM 7 or ARM 9 or ARM 11 or ARM Cortex, for every process, every ARM process, the programmer's model, there are only 15 registers, R0 or 15. So that is why it is common. That's why I'm taking LPC2148 as a fundamental, which is reference. Okay. So there is no separate program counter. R15 is used as a program counter, and there is no separate stack pointer. R13 is used as a stack pointer, as you all know. Okay, and there is something like link register, which is R14. So R13, R14, R15 can be used as a special function registers, and the remaining registers from R0 to R12, those 13 registers are used for general purpose, where hence it is reduced instruction set computing with having more number of registers. And there are different modes, as we all know very well. This is user mode, and there are something like user or system mode and fast interrupt mode, supervisor mode, abort mode, etc. This is the very interesting thing you need to understand. Okay, so this is so beautiful, right? And this is the code that what you have written as usual, and the assembly language program for the same C program. The compiler has written an assembly language program for this. And if you see for while one, we have written IO1 pin equal to 1's complement of IO1 pin. So for that, it has written an assembly language program, ARM 7 assembly language program or ARM assembly language program. You see the first row, there is a direction register. Because the direction registers are configured as 0, so it is acting as an input port. So when the direction registers are acting as an input port, so none of the pin will get affected. Okay. So if you want to make the port as an output port, we have to make the direction registers as logic 1. So when we make the direction registers as logic 1, the port will become output port. So whatever value we are giving, that will come out to the microcontroller. So we have never configured direction register, hence it is not blinking. That is what the model. Okay. So for that, I am just going to change the code. This is for you to understand the significance of direction register. That is why I have done this. I did this. So now it is very much important to make use of the direction register. So I am using the direction register. The configuring the direction register, which has to be done only once. Hence I am writing in between void main and while one. So IO 0 DIR equal to, that means input output 0 direction register equal to 0x. I'm going to make all the 32 pins as output port, right? So for that I'm giving FFFF. So I'm giving 32 ones. Okay, in hexadecimal, hence 8 Fs. 1 F equal to 11111111. Instead of giving 32 ones, I'm giving 8 Fs. Okay, this 8 F equal to 32 ones. What do you understand from this? All the 32 pins of the port 0 of LPC2148 microcontroller are configured as output port. After that, I am toggling means it will toggle. Let us see whether it is toggling or not. So after modifying the code, as usual, I am going for compiling, building, and rebuilding all. And as usual, I am going for debug. Oh, I have to check for zero error, zero warning. Yes, there is a zero error warning. So there are two warnings, but normally we never consider about warning, right? Okay, let us leave it then. Going to debug start stop. So I'm going for the debug session. And in the debug session, the same window has come. Now the program counter is pointing IO0 direction register. Default, it is acting as an input port, hence the direction registers as 0. Now by executing this fourth line, we are making the direction registers as FFFF, hence we will be configuring the parallel port as output port. Let us see. Now I am going to execute the first line, IO0 DIR. The fourth line was executed, IO0 DIR, and all the ones, right? You can see the direction register has changed from 0000 to FFFF. So all the ports are configured as output port. So all the 32 pins are configured as output port, and now you do the single step execution, right? Now you see while one, you see here IO1 pin equal to 1's complement of IO pin. Okay, now I'm going to execute the seventh line, right? And now the pins are 0, right? Pin value is 0. When I do the single step execution, pin value has become 1. You can see all the pin has become 1 because it was toggling, right? The tilde symbol is to toggle. It is 1's complement, right? All of us know that tilde symbol is 1's complement in C syntax. So port 0 pin is 1's complemented. Already it was 0. So because it is once complemented and written to the same pin, hence it has all the zeros has become 1. Okay. Okay. So once again we are running with it because it is within the while loop. So it has to blink, right? So you can see, look at the screen, the seventh line will keep on executing. So it is keep on blinking, right? So if you observe carefully in LPC2148, whenever the pins are 1, the set bit is also 1, right? There is a set register, right? IO1 set register, IO0 set register is also 1, so hence the pin is also 1. So whenever you want to set a particular pin, the set register has to be 1, which is very important, you need to understand, right? So when I run this code, so automatically it will keep on blinking, right? So just keep on blinking. So you are thinking that, okay, the three pins are not blinking and here the four pins are not blinking. We'll discuss about that in detail later. But as of now, you need to understand IO0 DIR is a direction register where when you give FF, it will be configured, the port will be configured as an output port. Because it is configured as an output port, within the while loop, you have written the toggling features of this IO0 pin. IO pin is 1's complement of IO pin. So earlier it was 1 and it has become 0. Then because it is 0, it has become 1. So this is blinking of an LED. So when you connect an LED, the LED will blink, and we can understand, okay, LPC2148 is in my control, because my interest is to send out logic 1 for a period of time and send out logic 0 for a period of time. And it is pin is in logic 1 for the assigned period and pin is logic 0 for an assigned period, and that is getting repeated. So periodically it is sending out the data because within the while loop. Hence the port pins toggles as you see in the screen. And if you connect an LED to that pin, LED will blink. When LED blinks, we will stop blinking. Fantastic, right? This is how we have to simulate LPC2148 microcontroller. This is the way you have to start using the LPC2148 Keil IDE simulation. So if I want to make 16 pins as input and 16 pins as output, right? This is how I can make 16 pins as input and 16 pins as output. Now let us see what happens. Compile well, debug start stop. Now you can see I'm just running this code. I'm doing the single step execution, right? Okay. If you see IO direction register, right? The lower order 16 bits are configured as output and higher order 16 bit registers are configured as input. So we can see only the lower order 16 pins will blink, right? So let me run this code. You can see the lower order 16 bits are blinking and higher order 16 bits are not blinking because these higher order 16 pins are used as an input port. The lower order 16 pins are used as output. Okay, so 16 outputs and 16 inputs. Fantastic. So 16 sensors and 16 motors. Fantastic, right? So when the sensor senses, the corresponding motor will switch on. Something like that, you can write the code. And a lot more wonders can be done. Then sky is the limit, right? So it is up to you, it is up to your application. It may be a central locking system, or it may be a parking lamp system. Those are all my assumptions. Similarly, you can think of infinite applications and you can simulate it and you can submit your dream ideas just like that by using the simulation, right? So the significance of direction register, significance of IO0 pin is being discussed very clearly by doing the simulation, right? Once again, you are very eager to know about what is the set and clear, right? Okay. So you can do the blinking by using the toggle instruction, or we can do the blinking by setting and clearing. And this is very important. I want to highlight it. IO0 set, I can say IO0 set equal to 0x 1 2 3 4 5 6 7 8. Okay. Then IO0 clear. It's very important. I want to highlight you all 0x 1 2 3 4 5 6 7 8. Even for clearing, I should make it as 1. This is very important with respect to LPC2148, right? Even for clearing, I should make it as 1. There is no use in sending 0 in a ARM processor, right? If you write a data 0 means there is no use, right? For even for clearing also, in the clear register, we have to make it as 1. This is also another coding for blinking, right? I am setting the register and I am clearing the register. Now I am just running this, you can see. It is setting and clearing. It is setting and clearing. Setting and clearing. Because only the lower order 16 registers, 16 bits are used as an output port. You can see lower order 16s are used as an output port. All the 32 bits are blinking, right? All the 32 bits are blinking, but out of which only 16 pins are blinking. Right? So all the 32 bits of set register is blinking, but only 16 pins are blinking, right? Only 16 pins are blinking. Why? Because only 16 port pins are configured as output port pin. So internally there are 32 bits are getting changed, but only 16 changes are reflected in the pins because only 16 pins are configured as output port. Okay, if you are not configuring those pins as an output port, then whatever changes happening in the set register and clear register, that will never get reflected in the pin, which is very much mandatory for a control applications where it will never disturb the peripherals attached to the port pin. Whenever necessary, you can enable the port pin as an output port, and then we can send out the data to the corresponding peripheral. So the direction registers are more convenient for us to more use those port in more efficient way. That is the one you need to understand, right? Okay, just by changing the direction registers as all the pins as output port. Right? Say for example, as you see here, I'm changing all the port pins as output port pin 1 2 3 4, and I just compile well, debug start stop. Now you can see I'm just running the code. All are blinking, right? To set and clear, I can set an individual bit, I can set a clear an individual bit. For setting also I have to give FFFF, for clearing also I have to give FFFF. Okay. So there is no meaning in writing 0 to any of those registers. Okay. Only writing 1 to the clear register will clear the corresponding bit. That you need to understand. That is the beauty of ARM. Okay. This is applicable for all ARM processors, ARM Cortex A, ARM Cortex R, and ARM Cortex M. It is a good way to begin Keil, because the LED is blinking in the simulator window. What you can understand, what we can understand here is, now it is very important and very interesting, right? Now we can understand the ARM processor inside LPC2148 microcontroller is working, and the program that what we have written is there inside the flash memory of 512 KB, because the program has entered the flash memory of our microcontroller. So flash memory is being utilized properly. And because it is a memory mapped registers, right? Port 0 are the memory mapped peripherals. So those memory mapped peripherals are in the RAM, because it is rewritable memory. So ARM processor is working, flash memory is having our code, and the RAM is the memory mapped register where our port 0, IO set register, IO clear registers are there, and the memory content are coming out to the peripheral through one of the peripheral, which is parallel port, which is called the general purpose input output. Through this general purpose input output, data is coming out from the microcontroller, where we have simulated it. If necessary, when we connect a board and then we connect an LED, then we can able to see the blinking of an LED in the real world environment. If we replace LED with the corresponding motor, motor will switch on and off. If we connect a lamp, lamp will switch on and off. With the necessary hardware interface and intelligence, we can make an embedded application. Okay. It's very important. Even blinking of an LED is also a good good embedded system, where just by switching on an LED and switching off an LED, the traffic constables, that is traffic signals, are working well, and they are earning lots and lots of money just by switching on the green lamp, switching on the red lamp, and switching on the amber lamp at the regular intervals. So what interval is the challenge for that? They're being paid much. That's very interesting, right? Okay, so that is why we have to celebrate the subject. How now you can see there is an ARM microcontroller, out of which you have seen one module, two module, three, four modules, right? Now we have seen four modules are working through the simulation. Okay, that's all for now. Now it's fantastic, right?